Well, first of all, it didn't save where I was. So we're gonna have to go back to this part and begin.
But now, instead of just...
Hello, everyone. Welcome to something I already started the reaction of this. This is Simon Tracer, and I am going to analyze what the hell I'm looking at with this, because it's
measuring them with a Stern Gerlach machine like this, the experimenters get a choice about how to orient their machine. The three different choices are 0 degrees, 120 degrees, and 240 degrees. This is the twist on the EPR experiment. The experimenters get to choose independently. So the electron might be measured at 0 degrees, while the positron is measured at 240 degrees. If both experimenters happen to choose the same axis, then we know what happens. They have to get the opposite result as each other to conserve spin. The interesting case is when the experimenters happen to choose different axes. The number we want to predict here is the disagreement rate, the probability that the electron's result is different from the positron's. At first, let's see what quantum mechanics predicts for this number. Let's say the electron is measured with the 0 degree axis and comes out as plus. Now that its spin has collapsed to positive z, the positron spin needs to instantly collapse to be negative z. This is the non-local part of quantum mechanics. But what happens when this positron is measured by a machine tilted at 120 degrees? You can see that the positron spin is already almost facing the plus end of the machine, so it's much more likely to go to plus. In fact, there's a 75% chance it goes to plus and only a 25% chance it goes to minus. So the disagreement rate is 25%. And we can show that for any two different axes the experimenters select, the geometry is analogous. So they all have this same disagreement rate of 25%. Anytime the experimenters choose different axes, they will get the same outcome 75% of the time and different outcomes 25% of the time.
Now let's consider the local hidden variable alternative theory. The particles here are on a mission. Their aim to make you believe that they're acting according to quantum mechanics.
Alright, so that little eyes is like, I'm not so sure about this. But it's probably gonna close his eyes or whatever. When leading back to the diagram of axis and the attractive points, you forget
a machine tilted at 120 degrees. You can see that the positive...
You have to understand that the electromagnetic flow, again, just imagine that you had there's already been a video that talks about there aren't really four different possible, like the spin up, spin down, and the positive and the negative charge variants, because the variant that is supposedly spin down and negative charge is actually just a flipped over version of a positive variant, or the original variant. So in one of those charts, you only have either spin up positive charge, spin down positive charge, spin up negative, spin up positive. Right? Or whatever the hell up positive negative, down positive negative. Right? So here's the thing. Up positive is the same as down negative. It's just turned around. So its behavior is the same. Now, you can imagine that you're not even making anti-electrons in some cases, because if they have the opposite particle quality, it's just an inversion, but it's not really an anti-version because it's just oriented differently. And it's the whole thing that I go back to constantly is two cogs meshing together when they're propagating. When you make the two particles in the first place, one goes clockwise, the other goes counterclockwise. So similarly, and the thing about charge, and you notice that it's very interesting to think that the direction, simply based on the idea of orientation, is that you still end up with charges that will differ in their motion, and they're more likely to do one thing than another. And that's because the total amount of positive force that leads it to go from the middle down is the greater force of it attract moving energy that way, and also it moving that way. But the negative has equally a different kind of flow, and that negative is actually just the back end of the thing. So it's a quarter of the time as likely because of the variance of when you take one thing that is aligned with its, and the other one is aligned not exactly with it, you end up with, depending on their direction, the amount of space or whatever else, where exactly their positions were compared to the experiment when they got divided, or when they as they approached the device, that more than anything, and their orientation, determines how they will behave. But the one that's colored red literally is the same as the one that's blue, it's just upside down. So it's an incorrect interpretation. One is supposed to be clockwise and the other one is supposed to be counterclockwise, but the charges would be the same. Or the one is supposed to be, they're supposed to spin in the same direction, but their charges would be opposite. These have both charge and spin be opposite. So just flip your screen around with the phone, you can easily see this. They're moving in the same direction, like their structure is moving them in the same direction. So, but the other thing about positive and negative isn't that it's just positive charge or negative charge, it's that the positive variant of the electron has a completely different makeup than the negative charge regular electron. So yeah, it should skew, but whatever.
positron spin is already almost facing the plus end of the machine, so it's much more likely to go to plus. In fact, there's a 75% chance it goes to plus and only a 25% chance it goes to minus. So the disagreement rate is 25%. And we can show that for any two different axes the experimenters select, the geometry is analogous. So they all have the same disagreement rate of 25%. Anytime the experimenters choose different axes, they will get the same outcomes 75% of the time and different outcomes 25% of the time.
Now let's consider the local hidden variable alternative theory. The particles here are on a mission. Their aim? To make you believe that they're acting according to quantum mechanics, when really they're acting locally. Now we are anthropomorphizing, but I think it is really useful to just imagine them this way. We're trying to figure out if it's always possible for them to use a hidden variable theory to get the same experimental outcomes as Copenhagen quantum mechanics, or if in this new situation, our scheming particles won't be able to fool us. You can think of it like this. Each of the particles is going to be asked one of three possible questions, and they need to decide on their answer while they're still together, so that they can coordinate on their strategy. When they're done figuring out a plan for how they would answer any of the three questions, they pack away those hidden variables into three sealed envelopes for each particle. The question is, what strategies should our sneaky particles take to make people believe that they're following quantum mechanics?
This is just absolute... If you don't Newtonian this motherfucker, you're not gonna get it right. And you'll have the variance all the time because you're not understanding what you're supposed to expect. And all of those 75%, whatever else nonsense is like, you're still not getting the physics of what's happening. And that's dangerous if you're trying to make, like, I don't know, certain types of engines, reactors.
Remember, quantum mechanics predicted a disagreement rate of 25%, and so our particles want to match that. Whenever they happen to be asked different questions, their answer needs to disagree about 25% of the time.
No.
About 25% of the time.
So the thing is, what you're not understanding is the relationship between the particles and how they are functioning versus the objects that you're putting them towards. And that simple understanding can give you, and also the nature of the electron versus the positron. But God damn it.
What's the best strategy? Well, there's actually only two things that they really can do. The first strategy is this. The electron answers the same way for each of its axes, and the positron answers in the opposite way. Let's say the electron answers with minus, and the positron with plus. But this is a terrible idea, because whatever two different axes the experimenters happen to choose, the disagreement rate is 100%, which is very different from 25%. And so that strategy doesn't work. But there's only one other strategy that
No, because you're thinking that your equipment is 100% accurate. It's not. The variance of a micrometer is enough to make the electron move more towards the negative versus the positive. And if you compensate for that, you all understand exactly what's going on. But you're not. Some reason, don't know why.
particles could use. Instead of the electron doing exactly the same thing for all three axes, it does the same thing for any two of its axes, and then something different for the last one. Let's just say, for example, that it does this, and then the positron does the opposite. This is just one example, but it turns out for all possible strategies like this, the disagreement rate is going to be the same. Let's imagine first that the experimenter who's measuring the electron happens to measure it in the 120-degree axis, and it gets the answer minus. They make this choice a third of the time. And now, to calculate the disagreement rate, we need to see what happens when the experimenter who's measuring the positron happens to measure a different axis from this one, so one of these two. But in either one of these cases, the positron is also minus, and so the two answers agree with each other. And so the answers have no disagreement. And so we can multiply this by 0. But 2/3 of the time, the experimenter who's measuring the electron will happen to measure it in one of the other two axes. Let's say this one. The experimenter measuring the positron will measure in one of these two axes. But you can see that they only pick an axis that disagrees half of the time. That's 1/3, which is roughly equal to 33%, which is a different number.
I mean, you would think it would have to do with the direction of its spin, and so if you're making a system that has the positive be down, but the direction of it is down to the left, then if the spin is say to the left, then that means a negative. If the spin is to the left, then that will make it positive. But this other thing, you don't understand. There are it's not as clear cut as there's only one or the other for either one of the particles, although you're trying to figure out which one is doing what. By the time you finish your experiment, it doesn't matter if you know what it was, unless you know how it was made. And then you can know how to recreate it. But you're literally getting random, and then you're expecting things to be correct. So if you compensate for spin, if you compensate for positive and negative, then it makes sense why they go those directions instead of guessing or assuming.
From the quantum one. When our scheming local particles are interrogated, their answers for different questions match just a little too often. They simply can't fake the results of Copenhagen quantum mechanics.
So Bella's proof showed that non-local and local theories make different predictions about how often the two results will disagree when the experimenters measure different axes. Non-local quantum mechanics predicts disagreement only 25% of the time. Local hidden variables predicts disagreement at least 33% of the time. So to find out if there really is a local hidden variable theory, you just need to do the experiment.
Guys, 3 days into this game and I...
Okay, so welcome at the Institut Optique. You are here in the place where Alain Aspect performed 40 years ago his experiments on the measurement of Bell's inequalities, and here are some of the original pictures of this experiment, which was much more challenging than it is today, and it was a real experimental tour de force.
Okay.
So is this one of the original equipment from that?
This is one of the polarizer. It looks like that now. So only on this small breadboard, right? It's our main source. And this beam is directed towards this element, which is the key element of the setup. So it's a pair of crystals that produces pairs of entangled photons. We will produce a pair of entangled photons, and both are propagating along each of these two arms. They are separated. So here we have the two detection arms, and we can rotate the half-wave plate to change the orientation of the measurement basis.
Right.
The experiment that we did with light was a little bit different from the one we described earlier with electrons and protons.
Well,
so I'm going to explain how they...
Anti-light is not the same, or anti-electrons or protons isn't the same as splitting light, because splitting light is still the same thing, just going in different directions, doing something else. Anti-electrons have different values, or positrons have, like, I think different mass or something
correspond.
as well.
Here's a little diagram.
Whatever. What are you doing?
Of the measurement basis.
Why is the internet being slow?
The experiment that we did with light was a little bit different from the one we described earlier with electrons and protons. So I'm going to explain how they correspond. Here's a little diagram.
Well, shit. Do we have to do a third video because it's not letting me do it? Like skip or something. Ugh. Why is it broken?
So first we have this element that makes the entangled
Why
pair of
it
particles.
broke like that?
So that's these two. Then the entangled particles go off on separate arms of the experiment. In our previous experiment, we could decide the direction that we're going to measure the particles in by rotating the Stern-Gerlach machines. And in this experiment, it's actually really similar. So we have these two polarizers that we're able to rotate independently, and that is going to decide which direction these particles are measured in. And so this experiment with light is completely equivalent to Bell's experiment.
Bell expected that the experiments would show that the predictions of quantum mechanics were correct, and that there was some kind of non-locality in nature.
Before the first Bell test was done, John Bell said, in view of the general success of quantum mechanics, it's very hard for me to doubt the outcome of such experiments.
You didn't expect quantum physics to be wrong, because who would bet against quantum physics? You'd have to be crazy.
Remember, the two different outcomes for Bell's theorem depend on how often two different measurement axes are going to have results that disagree with each other. Here's how we measure that disagreement rate. First, we're going to start with both of the measurements being in the same direction. And now we expect that these two are always going to disagree with each other because they have opposite spins. So we're going to create a bunch of entangled particles and find out how many of them disagree with each other per second. This is going to give us a measure of the total number of particles coming per second. That's because this device is making loads and loads of entangled particles, and so we just need to know how many of them are coming at a time. Then we rotate one of the axes, and now we measure the number of disagreeing pairs per second. And then dividing these two will give us the disagreement rate. And remember,
You realize they have done all sorts of polarizing light things. Usually when you twist it for regular light, it just makes it darker, so less and less light goes through. So for this reference to light, it's not exactly at all analogous to the thing that is with electrons, because they have different properties than what light does.
quantum mechanics predicts that the disagreement rate will only be a quarter, whereas local hidden variables expects this number to be a third.
So I started at 2000, right? And now I have 500. So that really works really well.
We did do this experiment again, and the number we got very much agreed with quantum mechanics.
Sure.
But this is one of the most misunderstood experiments in all of physics.
No, it's
You
not.
will find in all sorts of physics
You're still not understanding the double slit experiment. Shush.
textbooks and papers and whatnot that what Bell's theorem proves is that it rules out local hidden variables or local realism. John Bell said that was an error. He said it's really quite remarkable how many people make that error.
I always get confused at the conclusion of Bell's theorem.
Yeah.
Because there's a lot of people who say, okay, it rules out hidden variables, or things have to be non-local, or whatever. But what do you think?
Yeah, I think it is super confusing. And when I first learned Bell's theorem, I was told that it rules out local hidden variables.
I've heard this other argument that it sort of disproves either locality or realism.
If you say, okay, it means that you give up local realism, and so that means you somehow have a choice between giving up locality and giving up realism. If you're giving up realism about what? You gotta tell me, because for most definitions of that word, you'd also be giving up locality. So what the hell are you saving? I just don't. Yeah, it's a really deep misunderstanding that shows up in almost every single textbook on the subject.
So what does Bell's theorem really prove?
Or better yet, what was Bell's theorem actually trying to convey? What is the...
Prove. Well, here's the logic. Start by assuming locality for the entangled particles. Using the EPR argument, the only way for them to coordinate their outcomes is using local hidden variables. Then, Bell's proof showed that local hidden variables predict an incorrect experimental result. Therefore, the assumption of locality must have been wrong.
We're obliged to invoke something like actions going faster than light from one place to another.
You still need to be accurate to the nanometer and beyond, and also accurate to like a billionth of a second. And you say you are, but the accuracy of measurement in spatial like exactness, it's really easy to think that you're completely accurate, but again, if you're wrong by, I don't know, the width of an electron, you're going to get different results that have absolutely false positive, false negative results, whatever. Like, whatever you're getting could be completely irrelevant information, but you're getting something that's consistent. And you still believing it is the thing. Instead of... No, I do question, because the thing is, the mechanism of transformation from a single item to something that is these quantum entangled particles, what the heck is going on in that base level? Is it possible that they're being maybe nudged or whatever else? And again, as they're moving with respect to if spin has anything to do with how they move, then you gotta consider that. Or if their polarity has something to do with it, what if they switch polarity immediately so that they orient themselves along with your devices? And the most powerful flow is obviously going to be in the direction of charge travel. It's really unlikely to move towards the negative lead where everything's being pushed away from. But the flow that you're most likely to connect with, and you have to understand, it is still a fluid you're working with. You're exciting things that are around you with these photons or electrons, both. More with the electrons. But there's things like the mass involved and whatever else. And you say stuff like 25% or whatever. And that's based off of certain numbers, certain things that you're allowing to include and exclude for some reason. And instead of looking at all data, somehow it looks like you're almost cherry picking, which is like, wait, why would you even do that? What is the reason?
The EPR paper by itself had shown that the Copenhagen interpretation is non-local, which is why Einstein thought there must be an alternative way to describe the experiment that is local. But Bell's theorem says that's not true. Any theory that correctly describes this experiment must be non-local.
But I would hesitate to say that means that Einstein...
Well, I mean, non-local could... Local simply, when you only look at one part of it, local just means the effect that started the process of the splitting of the, electron into the, or the photon, the gamma ray into the positron and electron. versus when you do it with light, it is a different process. You're working with a different type of quantum phenomenon than the electron, because one is energy that is polarized, has its own orientation and things differently. The electron itself is a little bar magnet spheroid thing.
Wrong, right? Because what I would say is this shows that Einstein was right to be concerned about all of this.
People often claim that Einstein's problem was that he simply couldn't accept quantum mechanics.
No.
It was only because he refused to shut up and calculate that he discovered two of the most important aspects of quantum mechanics: entanglement and non-locality.
The heart of the debate between Einstein and Bohr was about whether there was a problem, whether there was something to be concerned about. And the major concern that Einstein brought to the table from the beginning was about locality. But you know, what Bell showed was, oh yeah, all that stuff that Einstein was concerned about locality, he was completely right to be worried about it. We have a problem.
If these particles really are acting non-locally, this should cause paradoxes, shouldn't it? Well, it does, but the paradox seems to be surprisingly tame. Imagine you and your friend are measuring a pair of entangled particles. Suppose an observer sees you measure yours first, and then your friend measures hers. That observer thinks that you collapse the overall state of both particles.
I think if you have random variance and again, you're getting a lot of random results. Maybe you're just not understanding the physical properties of electrons as they go through your process. On their scale, on their, like, with all the different components, as well as you're not thinking of the electromagnetic field properly still. And
your friend just finds out the result when she measures. But another observer will see the situation in reverse. They see her measure first and then you. To them, it was her measurement that caused the collapse, not yours. But who's right? Which measurement was the cause of the collapse, and which was the effect?
You can't stop. Don't think in those terms. That's ridiculous nonsense that doesn't mean anything.
It seems to depend on your frame of reference. This paradox is worrying, but it isn't as bad as the usual faster-than-light paradoxes. In relativity, if you can communicate faster than light, then you can exploit how different observers disagree about timing. If your friend who's on a rocket sends you an instant message, and you send an instant message back, in some frames of reference, your message can arrive before she even sent the first one. If your message says,
there is still, and I've looked into this from another person's video talking about such things, that you going faster than light, but then the light signal happens later or whatever else, you can notice them happening at a later point in your existence, but it's not corresponding. If you notice the message first and then the light signal, it really doesn't matter who came first. The events happen in a certain order. It doesn't matter any of that stuff. Oh, my message is Mach 5. Their message is Mach 6. Clearly, they're going to get the message to me sooner, and depending on my speed, or depending on whatever else, you're going to somehow say there's a causality issue. Or if I'm it's analogous to a person throwing a ball and one person is moving away at a meter per second, the ball is going to hit them eventually. And depending on when it hits is due to like all the factors of wind resistance, blah, 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 their speed, everything else. But a signal about the ball being thrown happens after it's thrown. It gets to you before the ball does, means nothing about anything. Right? You can hear stuff and then get the flash later. Impossible. The flash is always faster, right? But what if you hear the thing because the only way that you can get the information like earlier than the events happening is the ridiculous idea that time travels backwards. You're just hearing about it at 2 seconds instead of 1 second ahead of the event actually taking place. You're silly.
Don't send your original message, and so she doesn't, then you've got yourself a paradox. What prompted you to send this message if she never sent you anything in the first place? Quantum mechanics, science.
Again, and it's an order of events that still goes 1, 2, 3, 4, 5. Read that to me again.
Observers disagree about timing. If your friend who's on a rocket sends you an instant message and you send an instant message back, in some frames of reference, your message can arrive before she even sent the first one. If your message says, don't send your original message, and so she doesn't, then you've got yourself a paradox.
That's a flat out, complete lie. Instant message. Right. Sure. Okay. So, again, no one ever makes these assessments correctly, but what you still have to realize is you wrote the message, you pressed send, even if it's a femtosecond in the future, it's still in the future. And you get that information, and then your brain interprets it before maybe the light about something happening comes to you. But everything is still 1, 2, 3, 4. There's no time travel nonsense here. This is when, and it's neatly just pushed right in there, expected as true, random factoid, absolutely based on nothing.
What prompted you to send this message if she never sent you anything in the first place? Quantum mechanics sidesteps these paradoxes.
Listen, if you're going to have a message that can go back in time, right, you have to explain, well, okay, well, we can send messages back in time, grandfather paradox, blah, 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 blah. You can have these loops all you like, but even if there is a paradox or whatever, you first have to assess the fact that you're trying to explain that an event can happen before another event, and going faster than light doesn't make that possible. Again, if it takes 8 light seconds, 8 light minutes, entire minutes, right? for light to come from the sun, then an instant message saying the sun exploded, and then you find out about it 8 minutes later by observation, it's again the same as if you said, watch out, someone's throwing a football at you, and it comes at you, and then you notice it happening. You get the message way long before it happens, or whatever, but there's no difference between this and that. But as long as you're still saying it's going to happen, and then they throw the ball, and then your message gets there first, and then the ball ends up hitting you later, maybe you dodge it. Maybe you get hit by it when you turn around and see it. Or maybe you catch it. Or maybe you have enough time to throw another ball and hit them first. So they're timed out, and then, like in dodgeball, and then you're safe because you also caught the other ball, or whatever else. The idea of the ball will travel through the air at a certain speed, and it takes us less time to say it. And seeing it happen, right? The longer and longer away you are, the longer it'll take for that information of sight to get to you. So, again, it's just different forms of communication. It's the difference between the speed of sound and the speed of light, or whatever. There's no weird stuff happening.
Through a fundamental constraint. The outcomes are random, so you can't send messages faster than light. When you measure your particle, you get a plus or a minus completely at random.
Listen, if I sent a message that was twice as fast as light about the sun exploding, and then the sun explodes in 4 minutes later, or 8 minutes later, as long as I sent the message when it explodes, one, I'm dead, but you know about it and you can launch away, and if you're able to move away at the speed of light, you're never going to see that sun explode because you're going away from it faster, so fast that the light can't keep up with you. And if you move at 99.9 trillion nines the speed of light, it'll catch up to you, but it'll take a while. And if you're moving faster than the speed of light, you'll never know that you'll never actually see and witness the Earth exploding, or the Earth being affected by the sun's explosion.
Friend measuring their particle also gets a random result. Now the results will be correlated, but they're still completely random, so there's no way to send any faster than light message in this way. That's what prevents us from sending messages back in time using quantum mechanics.
No, you're not able to send messages back in time because particles don't go back in time. You're convoluted as frick right now.
So quantum mechanics is non-local, but it doesn't lead to the sort of catastrophic paradoxes you might expect from relativity. But it's an uneasy truce. Quantum mechanics may not break the letter of relativity's laws, but it certainly violates the spirit. And non-locality isn't the only troubling thing about quantum mechanics. The Copenhagen interpretation still doesn't explain what an electron is really doing, and why it acts so...
Yeah, that's because you're not thinking about how the electron is. You're thinking about it having a wave-like property, which it doesn't. It's a bar magnet being affected by the electromagnetic field that it is also affecting and exciting as it moves through space. So the EM field goes faster than the electron. As it goes through, it makes the double slit. So each individual electron, no matter how long between zaps, the EM interference pattern is there to make it, and it's based off of the telemetry, the shape of the holes themselves. Where the interference pattern is and how it works, and based off of the precise exit point from the gun of the electron is exactly where it will line up. And then, or also the other thing is, you have to think about the double slits are made out of, guess what? Matter. And all those matter have different electrons going around them. So unless you have some kind of special matter that is exceptionally neutral about how it moves and uniform, which is like a crystalline structure or something, or a magnetically charged or something structure somehow, or a superconductor, something, which you're not using, by the way. You're just using regular old metal or paper or something. And your fingers, or who cares? The point is you're making you're making the interference pattern, right? With the EM field. The electron is then governed by the pressure waves that are pressing on it from either side. So it only has the option to go and land here. There is no other component to it. It just is, always has been traveling to here. No other part of it exists anywhere else. Stop being silly.
Differently when measured. Despite this, many physicists took Bell's theorem to mean that the Copenhagen interpretation was right all along. Bell himself rejected this. He spent the rest of his life championing alternative interpretations of quantum mechanics, including the hidden variable interpretation called pilot wave theory or Bohmian mechanics. Bell's theorem does...
You mean the thing that I was just talking about, where you have an electromagnetic field around the particle? That's what that looks sort of like. And yeah, those waves going through will make the interference pattern and stuff, and it's not the electron itself doing those things.
Doesn't rule this interpretation out, because the pilot wave theory is non-local, just like the Copenhagen interpretation.
Shut the fuck up. The pilot wave theory, again, no, the EM field goes and is excited as the electron is moving through it. You can imagine it like if you have any fluid and you push your hands, waves can go in front of you further than your hands have gone. Right? The electron is doing the pushing, but the EM field is the fluid being interacted with. So when you've done fluid dynamics to make the interference pattern in water, in your older videos, you should have already understood how this works. How the electron goes through. It is basically the tip of your finger or your hand. It's not the waves. It's not the thing making the... It's not... It is the thing that is influencing the waves. But it is not the waves themselves. You are not water. Your finger isn't water. So, you're so lost in it, and somehow you're saying it's not a local effect. It is a local effect. Again, a lie. Flat out. Or maybe their idea of how pilot wave theory is whatever, then you got a wrong theory again. Go back to your electricity video, get some knowledge again, and then come back with an apology letter, which has to be signed, "I'm sorry, Simon Tracer, I got it wrong, You were right. A scientific rant. Or something. No, I just freaking need you to say, this is the theory that is correct. You don't even need to quote me. It'd be nice if you freaking did. I deserve a Nobel Prize for this shit. Just like anyone else doing the research. But actually having the understanding of it. Because when you actually look at the EM field, what it actually does, you will have the understanding of freaking the spread out of the universe, for example. As all items are sending out light, that's an EM field disturbance, and everything is affected by EM, so everything is nudged, and the amount it's nudged is based off of the intensity of the light, and its mass, polarity, and everything else. You'll find out why the EM field is the thing that is the background of galaxies, the thing that is flowing along with them, and makes it so that they don't just fling up and separate, but they are closely knit because of EM force. Because it's way more powerful than gravity, guess what? That's exactly why. But it's ironically similar to gravity in the fact that at a distance, all you're working with is the protons effect and the light and the electrons. And you have to think about how these things interact, not just how electrons excited work with the electromagnetic field. What about the protons and stuff? That is a completely lower effect, and it's equivalent to gravity. Very similar.
So I got this Count Dooku
Oh,
saber
yes.
from SWAC.
Local, just like the Copenhagen interpretation. It was Bell's theorem and Bell's subsequent tireless work that made studying the meaning of quantum mechanics respectable again. He showed that mere armchair philosophy and thought experiments can have real consequences in physics.
We need
Hey, I'm in an armchair. Could you actually listen to someone who knows what they're talking about?
to be teaching quantum physics in a different way. We need to be teaching Bell's theorem in a different way. We do often teach Bell's theorem.
Try figuring out proper theorems. Think for yourself and actually, like, remember what you've already learned, which is beyond all this stuff.
You, physics students, and it's taught us something that rules out local hidden variables. That's just not true. Bell's theorem, says that quantum physics is in very serious tension with relativity on the issue of locality.
John Bell passed away suddenly at the age of 62. He didn't know it, but he had been nominated for the Nobel Prize just a year earlier.
In a talk he gave in Geneva in January 1990, he said, "I think you're stuck with the non-locality. I don't know any conception of locality which works with quantum mechanics."
I do. It's called a particle of an electron is not just one thing, but it's it and everything it influences, which includes the protons of other atoms.
That was 8 months before he died. So pretty much his last word on the subject.
And so that's it. There really are faster-than-light influences in the universe. Bell's theorem proves it. But maybe there is a way out. There is another way to interpret quantum mechanics that's even more bizarre than the Copenhagen interpretation. Imagine the EPR thought experiment again. We can think of the entangled state as being in a superposition of the electron being up and the positron down, and the electron being down and the positron being up. In the Copenhagen interpretation, when you measure a particle and you get only one result, say plus, the other part of the superposition collapses. But in our examples, we've seen that measurement collapse seems to be the source of non-locality. So why don't we just get rid of collapse altogether? This is what the many worlds interpretation of quantum mechanics proposes. When you measure a particle, instead of you collapsing the particle to one outcome, both outcomes happen. And there's two parallel versions of you who see...
Yeah, now you're going into pseudoscience. So the thing about that is that there's a physical world out there where things actually have proper, structures. When you look at the electron properly, you'll understand that it has a structure, and you'll know what that actually is and looks like and operates to do, and you'll understand how it works with the EM field instead of ignoring the field's existence entirely, or at least partially. And you have to understand there is the chance that the particle is doing one of two things. Yeah. So whatever the initial state of the one particle, the other one does the other thing, because that's how cogs work. So if they started in a positive, the other one is going to end up being the negative. And if it started in a negative, or up, it's going to end up being down. Vice versa. That's just reality for you.
Each outcome. You have become entangled with your particle because your state depends on what the particle is doing. It sounds strange, but there's one huge...
Again, you're using the word entangled, but you're just having... There is a correlation of events. Entanglement is the terminology referring to things that are physically connected. Please, can you get your language correct?
Benefit of this interpretation. When your friend is about to measure her electron, your positron doesn't need to rush to tell the electron what the answer will be. There are already two versions of the electron, and they contain the right answer for each version of her. There was no need for faster-than-light communication to explain the EPR experiment. But how is that possible? Doesn't Bell's theorem prove that the two particles must communicate faster than light?
Set limits and stay in control.
Light? Well, in Bell's proof, we assumed that all measurements have just one outcome. But that assumption just isn't true in many worlds. This means that technically, that proof doesn't even apply.
The assumption isn't even true in this world because you get seemingly random effects because, again, you're not accurate to the billionth of a second. You're not accurate to a quadrillionth of a second. You're not accurate to the position of the electron through this thing itself. You're missing factors.
In the many worlds case. So is many worlds local? In one...
It's like you're bumping back and forth between, like, how many thought experiments can I throw at people without giving them any justifiable answer except for to say that it seems to be unlocal because we can't figure out why. Because you're not thinking about how to figure out why. Because you're not remembering what you've already learned. And that's disappointing.
Since no, because just like in Copenhagen quantum mechanics, entangled pairs can be separated by a huge distance and still share their state. However, it is local, unlike Copenhagen, in the sense that these faraway entangled particles do not influence each other faster than light. Many worlds obey.
Many worlds doesn't give a crap about the speed of light. It's happening simultaneously. The speed isn't the factor. It's the fact that it's all happening at the same time. Simultaneous. There is no difference in instances it just happens, right? That's the idea. It's just a ridiculous idea to shrug off and say we don't need to know because it will just be whatever because we can't figure out the actual thing. Now here's the thing about it. In a multiverse where you have these things happening, there are ways that you can do tests to then find out if you can get real answers from the other universes. Because of one thing happening triggers another thing, and depending on if you're right about all of your assumptions, depending on what it triggers, then you know you have now communicated with, or you've interacted with something in some universe that then makes the thing happen, that makes something other than what should normally in this universe happen take place. But the fact is we're having a lot of random. So if random is the thing, there is zero potential of proof of anything. So instead, you need to go back to your roots, figure out the structure of things, understand the basic fluid dynamics and the fluid you're working with, instead of being ignorant of it.
Is Einstein's universal speed limit. But is it really worth accepting that there are many versions of you in parallel universes just to recover locality? Well, locality isn't the only reason Many Worlds has become more and more popular. I also really like Many Worlds, because Copenhagen never sits, right? And when you start telling the story, right, of like what happens at measurement, it's like, well, what is a measurement? It's when you have like this quantum system and there's some other system which is like much larger, and so, you know, but it always feels a little bit arbitrary, whereas this argument that
the measurement system is simple. Depending on if it's the measurement of when the electron hit the plate, which lights up when it hits it, or if you have a beam going across the electromagnetic field and you see when it goes through, the double slit, but you also are removing the interference pattern because the EM field that you're shooting across the double slit is literally disabling the interference pattern entirely. It's like if you totally just shook all of the water instead of allowing it to make an interference pattern once it gets through the other side. There is then nothing pushing or pulling or whatever else doing anything. It's blank. No effect. So it just ends up with the distribution of it went through one slit or another, with variance of clearly some in the up and down, which also shows that if you instead had, I don't know, double slits that were bigger holes or whatever, you would end up with, or what if you made the double slits themselves, like the stuff that you're sending stuff through also has panels that can light up when stuff hits them. You couldn't, but every electron you've sent through goes through the double slit, hits the other side. You have a bing every time you shot, so something is directing them through besides your good aim. But there's a variance of an up and down, and that has to do with how it was shot out of the gun in the first place, meaning your system is not exact. It's not perfect. Or else it would all be in a center dot instead of a vertical lines. You're just not thinking about it right at all.
every time two quantum particles are interacting, their wave functions are essentially, combining and becoming entangled. That to me feels more consistent.
Yes, I think that's right. But what do you...
Like any light that goes through a medium, the two energies combine in ways, and then once it leaves, they decombine and go about doing their own natural thing that they do in open air or empty space, or instead of glass, now it's water or something. It has to do with what's influencing it, and when you remove that factor, it goes back to doing its own natural thing. There is no entanglement. It's like I can try blowing on the sail of a paraglider, and the sail might push up for a microsecond. I'm not entangled to the paraglider because of that, and its motion is probably not affected whatsoever because it just had a little bit of effect that made the sails ripple a tiny bit. Its motion is still relatively extremely fine, precise difference, if anything, if not completely, just not even changed. No entanglement whatsoever. It's so strange that people like, or whoever, are saying the word entanglement with vagueness and or lack of meaning that is anything to do with two objects that are actually physically connected to each other. You're just having some kind of cause and effect thing happen. It happened once. It's not a continued connection. It's not what. It's like how spells in the Souls games have lost their power because the grandiose of the deeds that happened back then are tales that have been retold and retold and retold so much that they have, and because no one has actual reference to what actually took place, they kind of are like Xeroxes that keep on getting ruined, and it just gets less and less potent over time. The use of the word entanglement has become like a buzzword. Zero actual reference to the reality of the thing. And it's just something used as a tag to get ideas flowing, to make it seem like, and if you seem like you know what you're talking about, it gets retention rate. It gets me to react for multiple hours on this video.
I think I like the problems with many worlds.
The biggest problem is, I think, people's struggle to deal with sort of the infinity that brings forth.
For sure.
But I don't know that that's necessarily an argument against it. Just because it's hard to imagine doesn't mean it's not what's happening.
The thing is that with many worlds, there are so many things that you can say should happen that don't happen. And have nothing to do with the simplicity of does an experiment happen one way or another. Many worlds also means all sorts of things, like does a supernova burst destroy the Earth or not? And in one universe, it did. It just flat out did, if it's real. So you have to come to the conclusion that I'm not in that universe because it hasn't happened. But every moment of every day in some random other universe, the other star randomly had some weird interaction and the burst came and wiped us out. We're lucky we're here. You want to feel that? You want to think that you're lucky to be here? Or would you like to know what the hell made the sun explode in the first place, so when it actually occurs here, you have some kind of idea, or just basic whatever, or ignore all of the possible ways that you could die, or whatever else, or things could go wrong, or things that could magically go right, and look at what's actually happening. Because there are just any number of things, right? Like just based on ratios, how many people could get cancer, how many people could get Ebola or whatever, or crazy plague, malaria and stuff and bullshit, and what are the odds of someone curing that? But then what are the odds of someone curing that and then being able to send a message in some way? Because the other thing about many worlds is that there is no disconnect. They aren't disconnected. They are intermingled. So whatever happens in a different universe, if they've solved cancer or whatever else, and if we listen enough or whatever else, we should get those informations if we're set up to get those informations from or whatever. And then we would just have that information. You're not thinking anywhere near what multiple universe theory, multiple world interpretation stuff actually would give us, if true. And it's so easy to just say these words when, if it did happen, there would be so many, like, hijacked signals or rewritten YouTube videos, because that's the thing people are paying attention to nowadays. If you want to be another universe and you want to explain to people how things are happening, you would, first of all, make a video and then have that video end up magically transforming all sorts of different times, so that when people watch it, they get different bits of information, like the lottery that happens in the future, or some nonsense. And ironically, if they get that information out to the correct universe, it's going to be right. But that's something that's easily able to be maybe just random, and it's a lot of noise to have to sift through, and it's basically the same thing as AI slop, and it makes it extremely hard to figure out anything. But what if one of those messages, instead of something stupid like lottery numbers, is an actual cure for cancer, or a cure for Alzheimer's, or a cure for freaking whatever thing we haven't found in the ice? First of all, it's this, that, and that thing. It has this structure, and also this is how you defeat it, because all you have to do is look at like these certain compounds, and the reaction of that makes this thing, and also this specific chemical and whatever else has this thing that happens when another part of what's already in your body to make a thing happen so that you'll just be fine. And then you do a random test based on that crazy information that somebody just shoved into the video randomly, and then it ends up being real. but then also explains, like, I don't know, open your mind. Realize we're alone. Stop grasping at straws. Great claims require great evidence. Carl Sagan. And me. Only I'm still here. What you're saying with the randomness is you don't have any evidence. In fact, you have non-evidence. That's about as close to misleading as I can think of.
If many worlds is right, everything changes. The conflict between quantum mechanics and relativity vanishes.
Again, if many worlds was right, you wouldn't be asking questions. You would have answers. Because certain ways to interact with them wouldn't just be ignored because of the assumption that it can't happen, but you would just have all of these different ways that it could tell you certain things, blah, blah, blah.
Physicists have been struggling for decades to unite quantum mechanics with general relativity to build a theory of quantum gravity. And maybe we've been failing because we've been trying to marry relativity to a non-local theory.
Maybe you want to hype it up. Quantum gravity is a spring returning back to its normal shape. It is proteins that like to fold in on itself and turn into a small little ball because that's the lowest energy state. Them being a crumple little thing instead of being stretched out. That's gravity for you on a quantum level. Springs, proteins. Crystals that like to keep on changing, the supposed time crystals or time liquids that keep on just shifting colors every so often because of the way the electrons going around with certain materials that are inside these liquids interact with the other parts to make this like constant flowing thing. I think it was Now Blue that showed this crazy interaction that just kept on switching from, it was ripples upon ripples and changing and changing, and randomness of, it was a bunch of orange that turned to ripples of blue, and it just kept evolving and kept being crazy. That shit is fucking awesome.
Today, I'm going to be doing one of the weirdest. Looks pretty even, and after that, I just have to wait. At first, not very much was happening, but then I started seeing some small little spots appearing. Even more of them.
This is freaking crazy.
And then started popping up, and they were all getting bigger and bigger. What's going on here is called a Belousov-Zhabotinsky reaction, and it's still one of the weirdest reactions I've ever seen.
This is the kind of random stuff that's like, it just keeps on going. The whole video was amazing. It's awesome. This is cool. And it's also quantum. And it's also random-ish, or everything affecting each other seems to be a thing that you do see how it progresses.
I'm going to be... And I started seeing some small little spots appearing. Even more of them then started popping up, and they were all getting bigger and bigger. What's going on?
And then you got this whole shock of blue that suddenly shows up. But also the ripples and how they affect each other.
Here is called a bellow.
And the bubbles that affect other bubbles is like an interference pattern that's messing with each other.
Usov-Zhabotinsky reaction, and it's still one of the weirdest reactions I've ever seen.
But it's because on the edges of everything there are these changes that are happening, and then after those changes occur, the remaining is the orange that is the norm, and everything else is just kind of reacting until it has nothing else to react to until the next wave comes in. And it just keeps on pulsing like that. It's freaking crazy.